Okay, sorry about the interruption in the previous slide. What I want to mention is that if we look at the equation 3.7, when we try to determine the sample size, and that depends on sy square, but we haven't conducted sample survey, how could we have the sy square? Very interesting. So maybe depends on if we can obtain the true variance from the population, then indeed we should use formula 3.11 to determine the sample size. Or we can still do our 3.7. If we look at the text, it says that if we don't have the true population sigma square, then we can still use a preliminary estimate of sy square, either by the past data. Let's say if we have done the survey from last year, then we can use the past data, or we can use a pilot study, like a two-step sampling procedures, or we can simply do a educational guessing. All right, so we can look at the example 3.5 to estimate the average amount of money for a hospital account receivable MU. We don't have any prior data to estimate the population variance, sigma square. But we know that most of the accounts that lies within $100 range. That's very important. Let's say the staff tells us that most of the account lies within that range. And the total population size is 1,000. And we know that we want to estimate the MU within a bound on error. So we know that the tolerance level, the bound of error is $3. So we're given that the range of most of the account lies within that, like a mountain. So most of the account lies within the MU plus or minus, let's say 2 standard, this is plus 2 sigma or minus 2 sigma. So we know that most of the accounts lies within this range. So we can say this is 2 sigma plus 2 sigma. Then we can divide by the range is 100 divided by 4. So sigma is estimated to be 25. Then we have the bound of error that we set up that equals to 3. And divide by the critical value at 95% confidence interval. So using 2 instead of 1.96. So we can estimate d squared is around 2.25. So let's use equation 3.10. Then we have the true n multiply sigma square divided by n minus 1 d squared plus sigma square. So this is around 217.56. So n must be greater equals to that figures. So we set an integer nearest to that. We need to round it up to 218. Example 3.6, we're interested in knowing the average household annual income in a city. The total household is 3 million, but we only have a sample size of like 10,000, giving an average household income of $14,000. And we're given a sample standard deviation is 4,000. What is the variance of average household and annual income? Since we can have the sample standard deviations, so we can estimate the variance of my sample mean. So this is a variance hat using the S square divided by n multiplied to the final population correction factor. So which is 10,000 divided by 3 million. We're given the sample standard deviation is 4,000, so we can put in here. We find the estimated variance is 39.92. What is the margin of error for mu given alpha equals 2.05? This is alpha. So margin of error, what we means is if we are plotting the y-bar distribution. So our y-bar is here at the 95%. So this is the margin of error, okay? So at a 95% confidence interval, so although this is both-sided, but we want to look at what is the margin of errors just on one side. So this is equals to the critical value 1.96 multiplied to the square root of the estimated variance, which is 78.24. So if we are looking at the confidence interval, then would be y bar plus or minus this margin of error. Like part C, find the 95% confidence interval. So y bar from the questions is given, plus or minus 1.96 times our standard error. So this gives us the margin of errors. So that means we have obtained the y bar from our survey, and we can be like 95% confidence enough to say that the true mu falls within this range. The range would be 14,000 minus 78.24 to 14,000 plus 78.24. D, suppose we do not have the sample standard deviations, so we don't have that 4,000. So we can guess it cannot be larger than 6,000. Again, find the 95% confidence interval. So we just substitute that 6,000 in here and find the confidence interval for mu. Okay, so comparing C and D, which is more precise? Of course, part C is more precise because the margin of error is smaller, right? So we are 95% confidence saying that mu fall within a smaller range of the errors within this. Whereas in part D, we're guessing the standard deviation is 6,000, so we have a wider confidence interval at that 95%. So mu is actually not shooting that correct as precise as the first case in part C. Example 3.7, if we're given population size, sample size, and some of the summary of the figures, you are asked to calculate y bar, which is summation of yi divided by my sample size. Then sy squared, that is the sample variance. Just to remind you how to calculate the sample variance, that equals to summation of yi squared minus ny bar squared. Okay, this is given, so we can plug it in here. Minus ny bar squared divided by n minus 1. Just to mention, previously, lots of students forgot to take the square of y bar here, so it ends up with the calculation having a very large sample variance. Okay, just beware. If we want to construct a 90% confidence interval for mu, then we use a y bar plus or minus the critical value at 90%, which is 1.645, multiplied to the standard error of our y bar estimate. Okay, so finite population correction factor multiplied to sy squared divided by n. Example 3.8, a survey on number of persons in a populations of 14,848 households is conducted. We asked only 30 households and then asked how many persons in your household. So we see that the one household having one member, 4 households having 2, 12 households having 3, etc. We asked 30 of them. Okay, so we calculate the average number of persons in the household, so that equals to the frequency multiplied to number of person plus frequency number multiplied to the person, etc., and divided by total household. So we want to calculate the total number of persons in those households divided by 30 households. So on average, that's about 3.47 persons in a household. What is the having one point estimate to describe about the population is not good enough. So we want to talk about the confidence interval. So what is the 92% confidence interval for our estimate? So we first need to calculate sy squared. Again, I want to remind you how to calculate the sy squared. with this frequency table. So that equals to the summation of yi square multiplied to fi, the frequency, minus ny bar square divided by n minus 1. Okay. The critical value, if you look it up, is 1.751. So just plug everything into the equations. We can find the confidence interval for mu. Just one more thing. If I want to estimate the total population size, so we can say that on average, there are about 3.47 persons in one household. Then if the entire population, we have 14,848 households, so the total population size is 5.473. So we talk about in the next session for the total estimate. Okay, I just put this example into an Excel file so that you can see y is the number of persons in each household, and how many households would have that number of persons. So that would be the number of households is the frequency. So it's the y-axis. Okay. Then the total household. Oops. Let me move that. Okay. Okay, this is the total household. Yeah, 30. So the average is the sum product of number of persons multiplied to the frequency, then divided by 30 households. The estimated variance of y bar. So we need to take the square of y and then to create a new row. And then we look at the sum products of these two and minus n y bar square, then divided by n minus 1. So this is the variance. Square root is the standard error of the y bar. Okay.